So we have a vapor power plant, and it has 25 kilograms per second of water circulating through the four components, being the boiler, the turbine, the condenser, and the pump. So the water flow goes this way all the way around in the loop, and those are the four components. It's operating at steady state, and the water flows blah 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 at constant pressure through the boiler and the condenser. So this P1 is equal to P4. It's constant pressure through the boiler. Likewise, that P2 is equal to P3, the constant pressure. So if you wanted to, a lot of times I talk about splitting the system, and this being the high pressure side, pressure high, and this being the low pressure side on that side, pressure low. And there's a pressure gain across the pump and a pressure drop across the turbine as it expands the steam. Okay, kinetic and potential energy effects can be ignored. So when we write a first law for the boiler, control volume around the boiler, or we do a first law around the turbine, control volume, or a first law conservation of energy for control volume around the condenser, likewise for the pump, we don't have to have those kinetic and potential energy terms with the mass flow rate. We just have to have the enthalpy with the mass flow rate. Let's continue to look at the problem. Process data is as follows. So the process 4 to 1, so this is 4 to 1, that's through the boiler. You could just say this is through the boiler, if you like, is constant pressure, and that pressure is given to be 900 kPa. And it goes from saturated liquid to saturated vapor. So coming in at state 4, it's saturated liquid, going out saturated vapor. Okay. Notice they give us a PV diagram, and they give us a dome. So what's at the top of the dome? The critical point. What's all these states over here? Saturated liquid on the left side, and all the states over here, saturated vapor. And you can see they kind of lined up the points. So 4, 4. So in the PV diagram, the state 4 is in the upper left corner, just like on the schematic, state 4 is in the upper left corner, and then the upper right corner is state 1 there. Then when you go through the turbine, you're dropping the pressure, and it ends up going into the dome at state 2, and state 2 is on the lower right side of both the schematic as well as the PV diagram, and then the state 3 is on the lower left side, both the schematic and the PV diagram. So basically at state 2, they're telling us that it's 20 kPa, kilopascal, and the quality right there, the quality at state 2 is 88%. That information's right there. And the quality at state 3, the quality at state 3 is 16%. So both states 2 and 3 are inside the dome, and the qualities are given. All right. So the first thing is, what's the cycle thermal efficiency? Well, we're in this chapter, we fell in love with this equation that 1 minus TL over TH, and a lot of students would like to use it, but there's nothing that says this cycle is reversible. It's not a Carnot cycle. And if we take a look at here, it's at part B, it's going to ask us for the sigma dot of the cycle in kilowatts per kilo. What's a sigma dot? Well, that's a strength of an inequality in the Clausius statement. And if that term is positive, greater than 0, there are irreversibilities. So this equation right away is like, no, 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 don't use it. Don't use it. Think about using it. You'd like to use it if it's applicable, but it looks like we're going to have to check to see if it's reversible or has some irreversibilities. If it has some irreversibilities, sigma dot cycle is greater than 0. Or if sigma dot 0 is negative, then we conclude it's not a possible cycle, it's an impossible cycle. It somehow violates the second law of thermo. That lines up very well with part C. It asks if the cycle is internally reversible or impossible. Well, if it's impossible, then sigma dot is less than 0. If it's internally reversible, sigma dot's equal to 0. And if sigma dot is greater than 0, it has some irreversibilities. All of these are for the whole cycle. Okay. So how are we going to determine the cycle thermal efficiency? Well, you don't use this equation from the Carnot, but you can use another equation. That is, the thermal cycle efficiency is what you desire. We desire a lot of power out or work out, W dot net. How's that? Over what we had to pay for to feed the cycle. And what we have to do is you have to burn some fuel to provide Q dot in to the boiler to make this power cycle work. Okay, so we just need to calculate the ratio of W dot net. Well, what's W dot net? Well, it's W dot for the turbine, and depending on if you do the W dot for the pump, now they use the arrow showing it's positive in. In that case, I would sometimes calculate this as a positive in, and then I would need to subtract it in this equation, W dot pump. But if you assume that it's positive out with a traditional sign convention for a control volume, then you should have put the arrow that way in the illustration, just like the arrow is coming out of the turbine. And then you would calculate a negative W dot pump, and then you would just add the negative W dot pump to the positive W dot turbine. So either way, stay with the sign convention or not, I'm going to do this. I'm going to change the arrow around. I'm going to have it coming positive out for the direction of the arrow for W dot, and then I'm going to actually have a negative W dot for the pump. Okay. And then the Q dot in, that is with our sign convention. It's positive into a control volume here for the boiler. Now, if you look over here, this Q dot out, I would change the direction. You know, if you're brand new to Thermo 1, change the direction of the arrow, and then know that this Q dot out is negative. So now I'm going to be calculating a negative Q dot out in the condenser and a negative W dot pumped in the pump. Okay, well, so I just need to calculate 1, 2, 3 things. How do I calculate each of those? Well, you just say, well, it's the mass flow rate. And if I do a conservation of energy around this turbine control volume, we did that in the previous chapter. We have steady state. You're bringing in this flow at enthalpy H1. You're taking it out at enthalpy H2. You find that it's H1 minus H2. Okay, what about the pump? Well, you have plus, because I'm going to stay that way, it's going to be a negative, and we have it coming in at H3, going out at H4, and we already know that enthalpy at state 3 is not going to be as large. It's going to be larger at 4, that's why this is negative. Okay, and then we have the mass flow rate times, for the Q dot in, I should have emphasized that. You do the control volume around the boiler, you have the mass flow rate going through. Q dot, it boils down to the H1 minus the H4. So it cancels, all of those M dots cancel. Okay, we're left with, I need to get those H's. I need to calculate the H's to get the enthalpies, and then once I have them, I come over here, and then I can calculate the thermal efficiency. Well, to help organize the work, put it into a table. A lot of times we just get lost organizing the information given and then the information we need to calculate. So I'd say state, and I'd put the pressure. Here we were given the pressure in kPa, so put that in the header. And then the temperature, we have our temperatures in degrees C. We're not given any, but because it's saturated vapor, saturated liquid, two-phase, it's all T-sats. The saturation temperature is only a function of pressure. And then we're given the qualities for 2 of the states, and then one is saturated vapor, one is saturated liquid, and then we can get the enthalpies. That's really what we want, the enthalpies, kilojoules per kilogram. So state 1, state 2, state 3, state 4. And what are our pressures? Well, 1 and 4 are the high pressure of 900. And 2 and 4 are the low pressure of 20 kPa. The saturation temperatures, they come in at 175.4, 175.4, and 60.06 and 60.06. But that's, so state 1, saturated, you can even do there. I'd like to put a little note to myself right over here. Saturated vapor. Well, you can treat it like a quality of 1 because you just need that H, or just look up Hg. H of G at that pressure comes in at 2773.90. Hey, what table did we use? Well, we've tested you over tables and being able to look up properties, but this would be out of table A3 as a little reminder. Go to table A3, get the enthalpy for saturated vapor at 900 kilopascal. Okay, let's continue on. We're giving the quality at state 2, it's 0.88. The quality at state 3, 0.16. Then the quality at state 4, where it's saturated liquid, is, that's H of, you can put a quality of 0 or just look up H of F, saturated liquids enthalpy. Let's report that value here, 742.83. Okay, and again, that would be out of table A3. All these you're going to use table A3 to look up the properties, because for the quality, it's two-phase, and it's two-phase. That's a P for phase, my notation, two-phase. Okay, so how do I get that enthalpy at state 2 and 3? Well, you just have the enthalpy is equal to HF plus the quality at whatever 2 or 3 times HFG, or H of G minus H of F. We've done that again, so we should be able to look up those qualities. You come back with 2326.7. I shouldn't say look them up, you have to calculate them. And then 628.73. All right, now that I have all those enthalpies, you just say, okay, here's H1, there's H2, H3, H4, H1, H4. And I'm going to, because I'm running out of room, just say you can calculate the thermal efficiency. And it comes in at 16.4%. That's the answer for part A. Box it and move to part B. So now, what is this term, this sigma dot for the cycle? Well, we're going to use the Clausius inequality. Well, what's the Clausius inequality? Well, it says that the integration over the cycle, that's why they put a circle right in the middle of the integral. Don't just do it for half of it, but do it for the whole cycle of the heat transfer. Sometimes I'll write like del Q divided by TB. It's a little funny notation, but this is thermodynamics. You're just summing up what is our heat transfer integrated over that boundary temperature, which you're having the heat transfer for the whole cycle, is equal to minus sigma dot of the cycle. And so when you had the inequality, it had to be or less than or equal to, and now you replace it to have an equality with the minus the strength of the inequality called sigma dot of the cycle. So now you take a look at the whole cycle and maybe even think about a larger control volume. Put a control volume like this. That's a bad looking control volume, but there you go. And you say, okay, was there any heat transfer to the surroundings with this pump over here? No, the pump is described to be insulated or adiabatic flow through the turbine and through the pump, meaning there's no heat transfer. Good. So none of there, but I have to put a control volume boundary right here, and what I have is I have Q dot N coming in, so in the boiler. So one of the parts of this integration around all the components for the whole cycle will be Q dot N. Maybe I even put the dot right there because I have a dot right there. All right. So it's a rate of heat transfer divided by the temperature at which it's coming into the working fluid in the boiler. Aha. Now we need those temperatures, don't we? But we don't just use the degree C. We have to convert the temperature to Kelvin. And so you can convert this temperature, which is a high temperature for the boundary, that the boiler's operating at, and it's 448.55 Kelvin. That's our T high. T high. Likewise, our T low, I'm fighting for space, always am. T low, 273.15 plus the 60.06, and it comes in with 333.21 Kelvin. And I do have the Kelvin up there. That's good. I have the Kelvin down here. That's good. All right. So that was for the heat in. And then what we're going to do is I'm going to put a positive Q dot. I know this is silly, but I would say, I don't know, put that boiler and this is condenser, because it's really going to be a negative quantity. Anyway, you have TL, and then you sum those up and you check it, because that's what we're trying to calculate. We're trying to calculate minus sigma dot of the cycle. Okay, for this problem, do I know my Q dot? Well, it's going to be the mass flow rate times the change in the enthalpy, H1 minus H4. That'll be the Q dot M, and I divide by the TH. Okay, this one I know it needs to be negative, or you just let the math work itself out. I'm going to add the mass flow rate, and if it needs to be negative, then I have the exiting enthalpy, H3 minus the H4, and then I divide by the temperature low, cold or high, cold or low, and that's equal to negative. If you want to, you can just put the negative sign on everything over here, and now you're just calculating sigma dot of the cycle. All right, well, do I know the mass flow rate? 25 kilograms per second. Good, so I know the M dots. Do I know the H's? Yeah, we used them already for the answer for part A. We have the temperatures. Notice they need to be in Kelvin, and if you look at the units, what's the unit right here? Kelvin, per Kelvin. So we definitely don't want to make that mistake of putting degree C in. And what we can do is we can just calculate this sigma dot cycle. So we calculate sigma dot cycle, and it comes in at the 14.2 kilowatts per Kelvin. Now, you say, that's answer for part B. You look at it, and then you say, well, if it was greater than 0, that would indicate that there are some irreversibilities in this cycle. We didn't say where. Could be in the boiler, in the turbine, the condenser pump, but there are some irreversibilities. From studying this a little bit more, they're focused in the turbine and in the pump, but that's okay. Or if sigma dot's equal to or less than 0, it's impossible. Or if it's equal to 0, it's reversible. Well, our case, sigma dot's greater than 0, so the answer for part C is it's irreversible. No need for an equal sign on that. Just box it. Just there's your answer. Okay. Now what I want to do is change this problem up just a little bit. Change the problem up just a little bit, and I come in and I say, oh no, change this quality at state 2. Change it to be not 88%, but only 80%. And change the quality at state 3 from 16 to 18%. So what it is, you're moving state 2 a little further this way in the diagram from 88 to 80% quality, and then you're moving state 3 a little bit further. Which way is it going? This way, a little closer that way. So state 3 moves there, state 2 moves there, and then you rerun the whole thing again. Well, you would calculate the thermal efficiency for the new problem comes in at 28%. 28%. You say, this is tremendous improvement. I was getting 16 miles per gallon. Now I did something, I get 28 miles per gallon with my car. Just sort of you see what the difference is. This 16% versus 28%, that's a huge improvement. That looks great. You come down here and you calculate the sigma dot of the cycle. What's the strategy again? You just do the whole thing. I know that you can do it. And then you would calculate for the new answer that sigma dot of the cycle comes in at negative 3.50. Well, what does that mean? Well, you can't have a strength of an inequality like that. You look for the answer for part C, you have to conclude that no. There's something that just makes that cycle impossible. At this point, you're looking at it and you say, well, that little change from 88 to 80% and from 16 to 18% on the quality, that's all you did? You didn't change the temperatures. You didn't change the pressures. You left this saturated liquid, this saturated vapor. But somehow that cycle's now impossible. There it is. That's the value and the benefit of thermodynamics. Sometimes it's challenging, but yes, that's true. So there you go. I'm done with this problem. Hopefully that helps. Thank you.